Hello, everybody. Teeth of the Lamb here, and today is May 31st of 2020. I've titled this video, What Makes the Moon's Face Rotate? The answer may surprise you, but the answer may really surprise you when you get the other half of the answer, and we're going to talk about that here today. One of the first observations that anybody that watches the moon for any length of time will find is that the face of the moon rotates in a clockwise rotation. And we're told, well, that's not really rotating. That's all just an illusion because it's stationary. Well, then they tell you the true cause is that you're on a ball and you're making an arc, and as you spin around the ball, and that causes it to appear to rotate. Apparent rotation, they call it. And that not only applies to the moon, but any other celestial object, such as the constellations. They also appear to make a clockwise rotation as they cross the sky. They do make equatorial mounts for telescopes and cameras that mechanically are geared precisely to take the rotation of the celestial objects out so they can make time-lapse photography. And they have to mechanically remove it. What's that tell you? And they'll try to tell you that that means that the objects aren't really rotating, that the equatorial mount proves it. That's not true. They have to mechanically remove it. We're told stuff like this. Water's not really flat. It's curved. Rockets don't really arc away from hitting the firmament. They really go straight up. Our pressurized atmosphere doesn't really need a container next to a vacuum. That only applies in a science lab and in the first law of thermodynamics. Another one. We don't really see too far. The equation 8 inches times miles squared only applies to other balls, not the ball Earth. And so you can boil it down to what you see and what you reason in your mind is an optical illusion. Don't believe what you see. And when you see the moon rotate, just remember it's not really rotating. That's just an illusion. We're going to accept the explanation that the arced path across the ball Earth is what causes the moon to rotate. And we're going to hold that lie as fact, so it can crumble under its own weight. Because what I'm going to show you is going to blow you away and prove it all wrong. Because they only give you half of the answer. That all sounds real good until you look at the rest of it. And we're going to do that right now. I've seen things you people wouldn't believe. So I went out and purchased a globe. I didn't have one. And it's kind of revealing when you look at it. Actually, it's very revealing. Probably why they put a sticker on the bottom of it, not for educational purposes, because you learn a lot by looking at it. I took 4 pictures from 4 different sides of the globe. One where it's tilting toward you, one where it's tilting away from you, and one from each side. And I did that because one thing they never talk about is the 23.5 degree axial tilt on that ball. And that changes a lot of things, and that's what gives you the arc for your moon rotation. But it also gives you a reversed arc. And we're going to look at what that does. But this looks fairly insignificant when you look at it. You look at the latitudinal lines, the ones that go east to west there, and they're straight. And that doesn't sound significant until you realize that as the Earth spins, you see the moon from this angle for about 7 days. And that is significant because with a straight line, the less the arc, the less rotation you get. That means for about 7 days, you wouldn't have any rotation whatsoever. And that's significant. Here the globe is tilted away from you, or away from the moon, because you're looking at it from the moon. So you can see the latitudinal lines, they've got a slight arc to them. But we see from 65 to a 180 degree rotation on the moon. That won't produce maybe even a 20% rotation. And that's just not enough because we almost always see the moon. It moves over a quarter of a turn, sometimes almost a half a turn, clockwise. And this arc, even though it's slight, does produce a clockwise rotation. That's what they say it does. And this is all they ever show you is this side anyway. You can see I'm actually at a very steep angle because you'll appreciate this, some of you. The continents are starting to disappear at the top of the ball over the curve. And so you can't go any further. You wouldn't be able to see the moon from all the continents. Again, this angle, the moon would be above this angle for about 7 days. Since the moon takes 28 days roughly to make its orbit around the ball, then you would have from each quadrant, or each of the 4 sides, you would see it for approximately 7 days each. And a little later on in this video, I'm going to make a chart. I'm going to lay out on this curve, I'm going to lay some rectangular picture frames on it, and I'm going to show you what that produces, just so I let you know that. I'll do that for the tilt away and the tilt toward the moon, because those are the two that really matter. Both sides just give you no rotation whatsoever. Now we come to side 2. Again, be 7 days roughly and no rotation. So now we've got about half a month, 14 days with 0 rotation. The moon always rotates. I have caught it a few times, but it's random, and it's about 4 hours where you don't see much for rotation, and that's very infrequently. Let's move on to the next one. And this one with the dipped arc, the reverse of the one that causes the clockwise rotation according to mainstream science. This one reverses that arc, and what you get is a reverse moon rotation, which is counterclockwise. We never see counterclockwise rotation, and so this is very significant. So far, we've got 2 sides that we've looked at, and they produce no rotation for about half the month, about 14 days. And then for about 7 days, we get a very slight clockwise rotation. So this is going to produce 7 days, roughly, of retrograde reverse moon rotation, which is counterclockwise, and we never see that. So that's very significant. It's not looking good for causing a constant clockwise rotation of the moon, is it? And this side would be, if you're looking at it from the moon, this side is tilted toward you, and so this causes reverse rotation, and the other one was tilted away from you that caused the clockwise rotation. Another thing I want to say is that the same problems apply equally to the southern hemisphere, exactly the same as what we're finding here, except you just kind of, when it's tilted away or toward you, they're seeing the forward rotation, and this is producing backward rotation on the northern hemisphere. So it'd be reverse, which kind of makes sense, but not really, because they still get reverse rotation just like we would, and so it doesn't work out very well at all. So as the moon orbits the Earth, you see it for about 7 days and 7 nights in each of these locations, because it moves so slow, 28 days roughly to circle the Earth once. And you can see here's a 28-day chart, and we took 4 different positions, and you have it tilted away and tilted toward in one and 2 sides. So that's all we did. And we just looked at it from each of those sides. And you can see them here. These are the 3 main ones. The side view on the bottom, tilted toward you on the right, and tilted away from you on the left. And here's which ones give you counterclockwise and clockwise and no rotation whatsoever. It's very interesting. We're going to go ahead and I'm going to lay out the charts, and you can look through them if you want, watch them to see how I derived the direction of rotation of the moon's face. The only 2 angles we're concerned with are the ones that create rotation, either clockwise or counterclockwise, and you see the one on the left, that's a downward arc, and it'll create a counterclockwise. The one on the right will create clockwise upward arc. This is what we're told is causing the rotation of the moon. When you take that path on the latitudinal line, I placed tripods on it, you're level with the Earth, so your camera may not be spinning. The ball is spinning, and that path is changing your angle of view of a stationary moon that's in the sky. So it appears to rotate in your camera, and the same thing with the constellations. Interesting, here are 4 pictures of Venus. Venus never rotates. So that's kind of odd, because any celestial object should be rotating. This is one from the UK, one from Oregon, one from Florida, and one from New Zealand. And they all give a slightly different angle, but they are stationary and fixed for the whole duration when it was setting in the west. And there was 0 rotation for the whole cycle. Now I'm going to go over my worksheets that show you how I derived at the direction of rotation for each of these arcs. Other than I know that reverse arc is going to give you reverse rotation. The worksheets that I have one for clockwise and one for counterclockwise, and we'll do it for each one. First we'll go over the clockwise direction. I'll lay them out on the curve itself and see how much rotation we get, and then I'll do the second one after I finish clockwise. Also, we're going to have, these are just some arcs that I drew, half circle, and we'll do each of these for clockwise and for counterclockwise also. First, real quick, I'll show you the rotating the camera is essentially what they're saying is happens when you follow the upward arc and the downward arc, that on a ball you end up with a rotating image in your screen when you're fixed level on a ball. So I'll go over that real quick to show you that. And we're going to have a flip in these charts, and I'm going to explain why we have to have that flip. This is the claim that when you're mounted flat with the earth, level with the earth, your camera is actually rotating on the ball left and right. And that's what causes the rotation of the image in the camera, even though it's level with the earth. I just thought I'd point that out. When I lay these images out on the arc, either up or down, we're going to have to flip them because we're looking at this chart from the angle of the moon. And when you're standing on the earth, you see it reversed. See, the image is flipped completely. So we have to flip our images, at least once anyway. And this is why, because when I rotate this, watch the moon and the numbers. Now they're facing the opposite direction when you look at it from the surface of the earth. So I just wanted you to know that so you don't think I'm trying to trick you and trade one lie for another. But you'd have to do a flip on it. But it's just easier to show it from the front side. From the vantage point of the moon is facing left, and the numbers are correct from 1 to 12. Then you go to the other side and you're looking at from the earth. Now the moon's the opposite direction. So we're going to have to make one flip, and that's it. Real simple. But this is why. Clockwise moon rotation. That's what they say we always have, and it is. When we look up, that's what it does. It's clockwise. And this is the arc that would cause that. But this is a insufficient arc to cause enough, 180-degree maximum rotation on that moon. So when I lay the images out on that arc, this is what we've got: west and east on the earth, and it'll be self-explanatory, I think. So I put a box on all the way across from 1 to 12 on the arc, and taken a stationary moon and placed it in each of those images, because the moon is supposed to be stationary. And now we're getting an angle on that arc. And then I'm going to take each of these boxes and put them up here above and level them. And we haven't done our rotation yet, because we have to do that because we're looking at it from the wrong side. We're looking at this from the perspective of the moon. So get each one of those up there. I sped it up. This would get extremely boring, and it may anyway get boring. But I want you to see how I derive to the conclusion of the direction. And now we're going to do the flip that I was talking about, remember? One way we're looking at it from the angle of the moon, and then we're going to switch to the angle of the earth. So we have to reverse it. And so I'm flipping each of these images just from right to left. And there we go. And then I'm going to explode that, zoom in on it, and you'll see that this produces clockwise rotation, exactly what it's supposed to do. Conveniently, they don't tell you about the angle of tilt of the earth, and that you would have a reverse rotation also. That's not important, I guess. Now I'm going to do the same thing, except I've done it with a half circle, and then you'll see we'll get a end up with a 180 degree rotation, and that's what we'd need. The very slight upward arc that we get when the Earth is tilted away from the moon, very, very slight, insufficient to produce the amount of rotation that we see. This is going to also produce the clockwise, but I wanted to do it two different ways to show you how it works. I'm rotating them, flipping them, I mean. And then I zoom in on it, and this is what we get. We get a clockwise rotation, but we're going to end up with 180 degrees. The less arc, the less rotation. The more arc, the more rotation. So we're coming all the way around, and we're at 9. Going to get a 180 degree rotation, half a turn. And that's what you would expect. Now we're going to do the same thing, but we're going to do it for the where the Earth is tilted toward the moon, and you get the dipped arc, the downward facing arc, and we'll end up with the reverse. I do want to stress that we don't see counterclockwise moon rotation. Not at all. The southern hemisphere does, but it's for them rotating clockwise. And we understand why, because they're looking at it from a different angle. So here we're going to do the same thing, but we're doing it for the downward facing arc, which creates counterclockwise. I'm placing all the images on the line in the boxes, which are angled with the line. And put them all up above. This was kind of boring doing it, but it's worth it, because then you really see what they're saying causes that rotation of the moon. And it's all bullshit. I mean, it's completely fabricated out of their minds, and they don't tell you all the rest of it. They only make it sound like, well, it seems reasonable if you don't think about it, that an upward arc is going to produce a clockwise rotation, and it does, but insufficient. And so here we go. We're going to number all of these. They're all in order, and now we'll have to go through and we'll do our flip. Remember, the reason that we're flipping it, we're looking at it from an angle of, we're drawing it out from an angle of the moon, a perspective of the moon, but we're going to be looking at it from a perspective of the Earth. And here we go. We'll just do our flip up here on the top. Yeah, it's a lot easier to see from the front side. It'd be hard to draw this out on the back side with dotted lines and stuff and try to show it to everybody. It'd get more confusing than it is. But there you go. We explode that out, and you're going to see we end up with counterclockwise rotation. And actually, that's a fairly steep arc. You get quite a bit of counterclockwise. So we're doing the downward arc when the tilt is toward the moon. Now we're going to do the other chart, the half circle, for the counterclockwise rotation. Just take each one of these, put the stationary moon in each of the squares that's angled to that curve. It's all about the angles. No less angle you have, the less arc, the less rotation. And if you don't have an arc, you have no rotation. So these will be in there in just a minute. Now we're going to do our flip. And then I'll zoom in on that line of images above so we can see what we got. Yep. Counterclockwise. Exactly what you should have. So I've done one on the actual angle on the globe, and then one with just a half circle. And this gives you the full 180 degrees. Well, I hope you enjoyed it. I hope you learned something. Leave comments, whatever. I'm happy to hear any suggestions. I've seen things you people wouldn't believe. And remember, it's all fake bullshit.